Recall that you can click on the timestamp in the description to skip this intro. It's generally beneficial to speak to one another live, as facial expressions and vocal tonality convey much that's lost over text, especially text that's limited to a certain amount of characters. That's one of the reasons for today's theolocution, with Sabine Hossenfelder and Bernardo Kastrup as the medium of Twitter has one's Twitter following requesting bloodshed. However, truculence pales in comparison to congenial, mutual constructiveness, and the latter is which theolocutions are, or at least what they are at their best. Sabine Hossenfelder is a theoretical physicist researching quantum gravity, as well as having the ever-elucidating YouTube channel, Sabine Hossenfelder, link in the description, as well as being a researcher, one of the prime researchers in superdeterminism. Superdeterminism is what brings us here today, at least thematically, and at most, inevitably, if the theory is to be believed. Bernardo Kastrup is the executive director of the Essentia Foundation. All links are in the description, by the way. Bernardo is one of the most cogent champions of metaphysical idealism, the view that reality is essentially mental, put forward with the analytical precision imbued in him from his PhD in philosophy and computer engineering. Click on the timestamp in the description if you'd like to skip this intro. My name is Joscha Bach. I'm a Torontonian filmmaker with a background in mathematical physics, dedicated to the explication of the variegated terrain of theories of everything, from a theoretical physics perspective, but as well as analyzing consciousness and seeing its potential connection to fundamental reality, whatever that is. Essentially, this channel is dedicated to exploring the underived nature of reality, the constitutional laws that govern it, provided those laws exist at all and are even knowable to us. If you enjoy witnessing and engaging with others on the topics of psychology, consciousness, physics, etc., the channel's themes, then do consider going to the Discord and the subreddit, which are linked in the description. There's also a link to the Patreon, that is patreon.com/KurtJaimungal, if you'd like to support this podcast, as the patrons and the sponsors are the only reasons that I'm able to have podcasts of this quality and this depth, given that I can do this now full-time thanks to both the patrons and the sponsors' support. Speaking of sponsors, there are two. The first sponsor is Brilliant. During the winter break, I decided to brush up on some of the fundamentals of physics, particularly with regard to information theory, as I'd like to interview Chiara Marletto on constructor theory, which is heavily based in information theory. Now, information theory is predicated on entropy. At least there's a fundamental formula for entropy. So I ended up taking the Brilliant course. I challenged myself to do one lesson per day, and I took the courses Random Variable Distributions and Knowledge/Uncertainty. What I loved is that despite knowing the formula for entropy, which is essentially hammered into you as an undergraduate, it seems like it comes down from the sky arbitrarily. And with Brilliant, for the first time, I was able to see how the formula for entropy, which you're seeing right now, is actually extremely natural, and it'd be strange to define it in any other manner. There are plenty of courses, and you can even learn group theory, which is what's being referenced when you hear that the standard model is predicated on U1 cross SU2 cross SU3. Those are Lie groups, continuous Lie groups. Visit brilliant.org/TOE to get 20% off an annual subscription, and I recommend that you don't stop before 4 lessons. I think you'll be greatly surprised at the ease at which you can now comprehend subjects you previously had a difficult time grokking. The second sponsor is Algo. Now, Algo is an end-to-end supply chain optimization software company with software that helps business users optimize sales and operations, planning to avoid stockouts, reduce return and inventory write-downs while reducing inventory investment. It's a supply chain AI that drives smart ROI, headed by Amjad Hussain, who's been a huge supporter of this podcast since near its inception. In fact, Amjad has his own podcast on AI and consciousness and business growth, and if you'd like to support the TOE podcast, then visit the link in the description to see Amjad's podcast, because subscribing to him, or at least visiting, supports the TOE podcast indirectly. Thank you and enjoy. We should be live. If you can see this, please type in Dexter's Lab. Dexter's Lab.
You're saying that to us?
To the audience, to the live chat, if you can see this, type in Dexter's Lab. So, Sabina, why don't you start with an overview of what superdeterminism is for people who perhaps aren't as acquainted as you are?
Okay, so superdeterminism isn't really a theory, it's a property of a class of theories which you find in the foundations of quantum mechanics. And they are designed to solve a problem, which is the measurement problem in quantum mechanics. More precisely, the problem is that in quantum mechanics we have an evolution law for the wave function, which is the Schrödinger equation that everybody who's listening has probably heard of. And then we have the update of the wave function, which is sometimes called the collapse or the reduction of the wave function. And this update is non-local, which means it's not compatible with Einstein's theory of general relativity. And now there are several ways people try to wiggle out of this. One, and that's probably the most popular one at the moment, is to say, well, it's just not a physical process. We're just updating our knowledge about something. Let's not ask about what, because that's where the problem starts. And that has its own problems, one of which is that it doesn't actually tell us what's happening physically. Like, I mean, we have to put something there if we want to take the expectation value of something. So just what is it that locally happens so it's compatible with general relativity? The other problem with this idea of updating knowledge and stuff like this is that we think of quantum mechanics as a fundamental theory that describes the constituents of nature. And that means that in its assumptions, there shouldn't be any macroscopic objects or other expressions like detector, observer, knowledge, and that kind of thing. Instead, it should follow from the theory. Now, you may say, well, the obvious way to fix this is just to replace this weird collapse with a local process that's compatible with Einstein's assumption of relativity and so on. And it brings up the question, like, why haven't physicists tried to do this? Well, the reason is that 50 years ago or something, they became convinced that this isn't possible, notably because of Bell's theorem. So Bell's theorem says basically, if you want a theory, to make a long story short, that describes our observations, which is local, like the way that we would want to have it, then it has to violate an assumption that's called statistical independence. And that's what's called superdeterminism. Okay, now you may wonder, well, why the heck is it called superdeterminism if it's about violating statistical independence? And I don't know. It's just that that's what it came to be called. A theory which violates statistical independence doesn't even necessarily have to be deterministic. And then there are a lot of philosophers who have gone on to claim that this requires some kind of conspiracy, that it would require us to throw out free will and so on. So it's been loaded with this philosophical baggage, which for me as a phenomenologist is completely irrelevant. You know, the only thing I want is I want a local theory that reproduces quantum mechanics on the average. So, oh yeah, I forgot to say this. So those theories which underlie quantum mechanics are hidden variables theories. So they say, well, the reason that quantum mechanics looks random, non-deterministic, is because there's some information which we don't know, and those are the hidden variables. And as always, I have to add that they're only called hidden because of some historical quirk in the nomenclature. It doesn't mean that they are unobservable. They may at some point become observable. They're just not present in the current formulation of quantum mechanics.
Great. And Bernardo, what are your thoughts on that? What do you agree with and what do you disagree with? Perhaps we can put this in the form of an amiable criticism where you start with the disagreements and then end on the agreements.
It's pretty easy to do because I agree with a great many things Sabine just said, and with the values that she espouses and fights for. And like her, the Bernardo of today, not the Bernardo of 20 years ago or 25 years ago, but the Bernardo of today is against metaphysical commitments in science, like the Platonic commitment that beauty is truth. So true theories should be beautiful and beautiful theories should be true. I got burned very early on with the supersymmetry, which we used to call Susie. I don't know whether it's still called Susie, but the idea is Susie is so beautiful. We all fell in love with Susie, so Susie needed to be true. It's not, at least not in the energy ranges where we can look with the LHC. Turns out it's not true. So I think it's a good value to espouse that science should be guided by hard-nosed empirical evidence, not by metaphysical commitments, by notions of truth and beauty being the same thing, and not by fantasy entities like the many worlds interpretation or the many hyperdimensional brains and brain collisions of M theory and all kinds of fantasies that are still put forward in physics. So I'm right with her in all these points. I do feel, though, that when it comes to hidden variables, Sabine runs the risk, or maybe is already doing it, of betraying those values. Because although it may be a historical quirk, there is a good reason hidden variables are called hidden. Nobody has ever observed them. Now, it's worse than that. Nobody has ever defined them. They are not even well-formed theoretical fantasies. Nobody said what they are and how they work. The only thing that is said is, well, if we want to safeguard certain metaphysical assumptions, then there should be these variables, we don't know what they are, that somehow, we don't know how, do what they need to do so we can stick to our favorite metaphysical assumptions. And in this case, the assumption is not determinism. I am with Sabine that I want to have a deterministic theory for single measurements, not only for ensembles. I want to predict the outcome of a single measurement. And everything we've learned in science over the past 400 or 500 years tells us that this should be possible because it has always been possible up until now. But the way to do this, I think, is not to reject what 40 years of experiments have been telling us, which is that a certain metaphysical assumption called physical realism is false. Physical realism is the notion that physical properties have standalone existence, that they were already there before you measured them, and that the act of measurement simply discloses what they already were immediately prior to measurement. There's another technical term for this, it's non-contextuality. Now, I think experiments have been telling us that this is not the case. And it's not that strange. Experiments are telling us that physical properties appear as a product of the act of measurement. Now, how can we understand this? Just think of an airplane cockpit. What is displayed on the dials is the result of what the sensors outside the airplane are measuring about the real world outside. If you don't make those measurements, there is nothing on the dashboard. The dials display nothing. Nothing is there. Does that mean that there is no world? Of course not. It only means that you're not measuring the world and therefore you see nothing. I think what experiment is telling us is that the physical entities we talk about today, the physical properties we talk about today, the observables of quantum mechanics, mass, angular momentum, charge, all those good things, they are the dashboard. They are not the world as it is in and of itself. They are the way a deeper layer of reality presents itself to us, how it presents itself to us. And therefore, if we don't measure, there are no physical properties for the same reason that if the airplane sensors don't measure the world outside, nothing is on the dashboard. The physical world is the dashboard. And I think heeding this and understanding what nature has been communicating to us after decades of consistent experiments is the way to find a deterministic theory for single measurements.
Sabine, what is your response? And feel free to speak directly to Bernardo. No need to say Bernardo or him, just say your, for example.
Well, you've been talking about what experiments are telling us, but how do you know what experiments are telling us? Well, you need some mathematics that extracts information from the data. And in your interpretation, you strongly rely on certain assumptions that go into the derivation of certain inequalities. One of this assumption is statistical independence. So if you don't have this assumption of statistical independence, then those experiments tell you something entirely different. Just to give a concrete example, how you can look at violations of Bell's inequality, and that's also, it goes the same way for all other kinds of inequalities, really. It doesn't really matter which ones, CH, SH, or Leggett's or what have you. They all make this assumption of statistical independence. So concretely, the conclusion which you can draw from the observed violations of those inequalities is that whatever is the right theory that describes nature must violate at least one of the assumptions. And normally people say, well, we assume that statistical independence has to be valid. Let's not ask right now why that is. Then it follows that local causality has to be violated. If you, on the other hand, say, well, we want the theory to be local, then it follows statistical independence has to be violated. And in my mind, that's the more promising way to pursue, because as I just said, locality is fulfilled in Einstein's theory of general relativity, and eventually those two theories have to communicate with each other, which is kind of a big unsolved problem, blah, 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 blah. I can talk about this for an hour, but I assume you're familiar with that. And also, maybe I should add, before I forget about this, all this talk about physical realism and so on and so forth, it goes past me, basically, because I would say I'm an instrumentalist. I care about what I can predict with my theory. If you want to call something about this real or not real or whatever, I'll leave this up to philosophers. Maybe on a very general level, I could say that in the hidden variables theory, the wave function itself isn't a real thing. It's some kind of an average value. It isn't any more real than the average person. That's not a real thing. That's a statistical thing. You can define it, you can write it down, but it doesn't really exist in the real world.
Right now, hidden variables theories are philosophy. You don't specify what the hidden variables are. You don't say how they work. You don't have an equation. I look at your path integral. The key term in your path integral, at least as of 2020, is quantumness, which is a placeholder for something you want to put there at some point. It's the key term because that's what you want to minimize. Nature wants to minimize quantumness, according to you. This is not theory, Sabine. This is not even the outline of a theory. This is a philosophy. Now, regarding
you're talking about the wrong paper. I hope if you excuse me for interrupting you, but this is indeed not a hidden variables theory, and nothing in the paper claims it is. You're looking at the wrong paper. The paper you should be looking at is called a local deterministic toy model, and it does have hidden variables. We explain exactly what they are and how you use them.
Did you specify what the hidden variables are?
Yes.
Did you precisely specify, so you can control for their state when you reset the experimental conditions in your experimental proposal? So you know exactly how to bring the hidden variables to the initial state.
That's a completely different question. You're asking, did I define the variables? No, I've defined them. I can tell you what the distribution is. Also, I mean, there's a reason the thing is called a toy model, because we made this up to prove a point, namely that those theories are not conspiratorial. You said there aren't any models. You don't know what the hidden variables are. I can tell you what they are. They are random variables that are uniformly distributed in the complex disk with radius 1. So you wanted an answer to this question. I should also add, that what you just said about there aren't any hidden variables models, it's just wrong. It's not that my model is the only hidden variables model that's super deterministic. There are others. We have the references in the paper. And, I don't want to be too hard to you on this because I hear this constantly. People are always like, super determinism isn't a thing, and they never bother to look at the literature to see what models people have actually worked with.
So you've made many points. Give me a chance to try to address not only one of them, but a few of them. Even if you don't like what I said about the first, you've made many points in a row. Let me try to address a few in a row as well before we go back to this. So let me do this in order. Statistical independence, you call it a mere assumption. I don't think it is a mere assumption. So let's try to illustrate for the audience what it means, what this technical term means. It means that the thing you're measuring does not change just because you set up your measurement apparatus in a certain way or another. For instance, if you are photographing the moon, statistical independence says that the moon will not change, will not do something else, will not be something else, because you set your aperture or exposure to certain values. The moon is what it is. It doesn't depend on the settings of the instrument you use to make a measurement of the moon or to take a picture of the moon. This is what statistical independence means. Is it an assumption? I don't think it is. I think the entire history of all of science tells us that this is how things work. Reality does not change based purely on the settings of what we use to measure it, what we use to photograph the moon. The moon doesn't change because I changed the aperture on my camera. Now you say that we cannot carry what you call an assumption. I don't think it's an assumption. I think it's a very, very solid observation, very self-evident observation about nature in all aspects of science. But okay, I will continue to call it an assumption. You say we cannot carry that assumption from the classical world to the quantum world, that carrying this thing over is arbitrary. But you are carrying something over from the classic world to the quantum world. You're trying to carry, and you don't like the isms, so I'm not going to call it physical realism. I'm going to specify exactly what it is. You don't want to carry the notion that objects have standalone, sorry, you do want to carry the notion that objects have a standalone existence, that they are what they are, irrespective of what they are, whether they are being measured. You want to carry that over from the classical world to the physical world. So I don't think you can have the cake and eat it too. Either you don't carry assumptions from the classical to the quantum, or you do carry them, and then you ought to carry a statistical independence because it's one of nature's most self-evident givens. Now, hidden variables themselves, unless there is something very new that you're springing on me right now, they are not defined. The experiment you have put forward is based exactly on the fact that you cannot reset the experimental conditions to what they were in the very beginning when you do a new series of measurements on the quantum system. That's why you talk about having to cool everything down, having to reduce the degrees of freedom of the measurement apparatus, having to do the series of measurements very quickly in succession because you're afraid that whatever state the hidden variables are in, they may drift. All that is based on the notion that you don't know what the hidden variables are. And we don't need the hidden variables for anything else in nature. Look, let's take the other variables, the unhidden ones, the ones we know, basic properties of physical entities. Let's take mass, charge, and angular momentum. If we remove them from the picture, we cannot account for any of the causal chains in nature, not only in a quantum experiment, anywhere. You take mass away, you cannot account for inertia. You take angular momentum away, you cannot account for magnetism. You take charge away, you cannot account for electricity. But you take the hidden variables away, nothing changes. We are still fine. So I think they are pure theoretical fantasies unless and until you can say exactly what they are, how they work, how they can be measured, and how they can be falsified. Because the experiment you have proposed by construction cannot falsify the hidden variables hypothesis. And I can elaborate on this at length to explain why I'm saying this. But okay, I'll stop. I spoke enough.
Yeah, we'll let Sabine respond.
Well, I noticed in your blog post, or whatever you want to call it, that you were trying to criticize the experiment that I proposed. Unfortunately, you don't seem to have actually looked at the original paper where I proposed the experiment. You quoted a paper from 2019, which refers to a paper from 2011, I believe, in which I have explained exactly how you can circumvent this problem that you don't know how the hidden variables, the state of the hidden variables in the prepared state. You make repeated measurement on the same system. And then I made some estimate for, what the size of the system should have to be, how cold it should have to be, and so on. Now, you're complaining that you can't falsify it, but of course, if no one makes the experiment to falsify it, then we're not going to falsify it.
No, my point is the experiment cannot falsify it.
So Sabine, can you respond to this unfalsifiable claim of the model?
You propose a model, and then you make a prediction, and if the prediction isn't correct, then you falsified the model.
That's not how it will work.
Of course. That's not how it will work. Yeah, well, that's quite possibly the case.
I can explain how and why.
If this is a general criticism about falsification, we can have this argument. We can argue that no theory has ever actually been falsified, if that's what you want to say. I would actually agree with this. The ether has never really been falsified, blah, 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 blah. As I've said a few times, we don't really falsify theories, we implausify them until people give up on them. But I think that's kind of a really tangential point.
So can I elaborate on why I made that
Sure.
claim? So first, we have to explain the experiment a little bit so people can follow. The experiment is the following. Since we do not know what the hidden variables are, we have to adopt certain procedures to minimize the chance that whatever they are, their values can drift. Because the experiment is based on the following. If you have a quantum system and you make a series of measurements on that system, according to the Born rule of quantum mechanics, you have a certain statistical distribution of measurements that is not deterministic. If superdeterminism is right, if there are these mysterious hidden variables, then the series of measurements will be determined by the system's initial condition. So the experiment is based on the following idea. Even if I don't know what the hidden variables are, and I cannot know how to restore the initial conditions of the system, because of course you need to restore the initial condition of the hidden variables too, even without knowing what they are, if I cool down the system and I make a fast series of measurements, stop and immediately do a next series of measurements after returning the initial conditions as best as I can, and then do the same thing and do another series of measurements, if superdeterminism is right, the series of measurements will all be determined by more or less the same initial conditions if I do them in rapid succession before the hidden variables have a chance to drift in value. And I will find time correlations between the series, which would then, if that's the case, contradict the Born rule. Now, because the whole thing is based on having to do with these series of measurements in rapid succession, but having enough measurements to find if there is a correlation between the series, you end up in the following situation. If and when the experiment fails and validates Born rule, one can always say, well, I didn't make enough measurements per series, so I don't know that they correlate, so it's inconclusive. Well, then you make more measurements per series. But then each series becomes longer, takes longer to make. So it will take longer for you to start the next series. And then one can say, well, it's just because the initial state has drifted. I took too long to do the next series. So whatever happens, one will always be able to claim that the experiment is inconclusive and doesn't falsify the hidden variables. Why? Because it's so loosely defined. We are not saying what the hidden variables are and how they work. We are not saying anything. We are just hoping that there is something that somehow does what it needs to do for this picture of nature, this metaphysical commitment that physical properties should have standalone existence to survive.
Well, two things. First, as I already said earlier, you're talking about the wrong experiment.
I'm talking about the experiments you talk about.
No, you were talking about a change in the initial conditions. I told you that the experiment you should be doing is repeated measurement of non-commuting variables on the same state. That alone is sufficient. In the 2019 paper, I was talking about a simplified experiment. I mentioned this in the text, and I can explain why I have reason to think that this is probably enough, but I'm not sure you're actually interested in hearing that. Okay, but...
Oh, I am.
Okay, good. I'll tell you. But so let me make a more general point, which is that you can't falsify superdeterminism. I totally agree with that, because superdeterminism is not a theory. It's a property of a class of theories. What you can falsify are specific models. And yes, you're entirely right. Those models would have to specify what the hidden variables are, or at least what their properties are. If you don't say anything about it, you can't make any predictions.
So what are the hidden variables?
Well, that depends on your model. You know, there are different models that people have put forward. I would say that at the moment, they're all unsatisfactory.
So according to your model, what are the hidden variables in your model?
In the model, which you already complained about with the path integral, we explained this in the paper. The hidden
but you said it was incomplete.
The hidden variables are the degrees of freedom of the detector, which are not the measurement setting. Okay, and now I can explain to you why I think that makes sense. Because I have a background as a particle physicist. Okay, so I don't like the idea of introducing new degrees of freedom and throw them over the already existing elementary particles in the standard model. You know this whole problem. You know, I get the impression you have some background in particle physics. So this is not a good idea. However, we know just empirically that the measurement setting affects the average value of the distribution. That's Born's rule. Okay, so that's the measurement setting.
You mean it's like the angular momentum you set, it will affect the distribution because everything will fall along the eigenvalues of the detector. Is that what you mean?
Basically, yeah. I mean something much more simple. If you want to calculate the probability of a measurement outcome, you have to say what is the thing that you measure, right? Otherwise,
okay.
how are you going to project it on the eigenstates? Okay, so that's that. But this brings up the question, like, what's with all the other details of the detector? What happened with them? Like, a detector is not just a measurement eigenstate. It's a complicated big thing that has many degrees of freedom. So the model that I'm trying to develop, which is the thing that you're complaining about with the quantumness, and that's the that's the discussion in the paper where I say this is the part which I haven't figured out, is exactly how those degrees of freedom enter the evolution law. But this is the idea. So the degrees of freedom of the detector, except for the measurement setting itself, are the hidden variables. And now once you buy this, and I agree with you that I don't actually know exactly what the evolution law looks like, you can very precisely estimate how long it will take. I mean, maybe not as precisely as I'm hoping, but in principle, you can estimate how long it will take for them to change. And that's why I think the simpler estimate in the 2019 paper is probably sufficient.
Okay, I will work with you. I'm really not closed-minded about this, but there are things about this that normally would trigger your worst part. And in this case, it doesn't, and it still triggers mine. However complex the experiment or the measurement apparatus is, if we are talking about local hidden variables, what matters is what the thing measured interacts with. The thing measured, say, you're looking at spin of an elementary particle. The thing measured is tiny, so it has an interaction with a tiny measurement surface of the same order of magnitude as an elementary particle. Everything else in the apparatus is about amplifying what's measured, say, photomultipliers, sending that signal and then displaying in a way that is cognitively amenable to a human being. But the measurement surface itself is tiny. So whatever is going on in the other degrees of freedom of the measurement apparatus shouldn't have a local causal effect on what happens on the point of interaction, right?
So I think we may just disagree on what we mean by detection or measurement process. I would say that the amplification actually is the measurement. Like that's what we need to convert a teeny tiny thing, like a single photon going through a beam splitter, into something that we can actually read out. And normally this process is described by decoherence. And that's also an interaction with many particles. Now, I actually do think that this process of decoherence that Zurek and Z have gone on about captures some part of the truth. You know, it tells you how the environment selects the pointer bases, but it doesn't tell you how the outcome of a measurement is always a detector eigenstate. In the normal decoherence paradigm, you always end up with a mixed state. I mean, generically, unless the state happened to be a detector eigenstate already. And so what superdeterminism does for you, what the violation of statistical independence allows you to do, is it allows you to write down a local evolution law that will bring the initial state into a detector eigenstate.
I agree with what you often say, that this notion that superdeterminism will invalidate the whole of science, that's nonsensical. I agree with you there. But what you just said, that the amplification of the original measured signal can determine the measure outcome. Now that sounds spooky to me, because you're saying is that, okay, there is an interaction between the system measured and a measurement surface, which is tiny. Everything else is just amplification and transmission and displaying the result of that measurement outcome. But you say something causally efficacious happens in that chain of amplification that actually determines the outcome of a measurement, not the interaction on the measurement surface, but the amplification of that. It's like the photo multipliers to give me a different energy reading from my tile colorimeter. Now, if that's the case, then I have to throw away all my experiments, because what I'm seeing is not the result of measurement, it's something the detector has done and distorted everything. How do you reconcile this now? We have to assume that amplification does not distort the result of measurement. So if you measured angular momentum +1 in a certain direction, then that is the reality of what's measured, and not something engendered by the photo multipliers or whatever amplification system you used in your detector.
Yeah, I'm not sure I understand the question. Like, so, I mean, you measure some variable, you measure the spin. You get a probability distribution that's the same as in quantum mechanics. Okay, so what those other degrees of freedom of the detector do for you is that they decide which the outcome is. So they don't change the mean value, the average, Born's rule. That's what you need the detector eigenstates for. They're the random variables that decide what is the actual outcome.
But then I go back to my original point. How can all this complexity of the detector influence the measurement outcome if the actual measurement happens on a surface area of the same order of magnitude as the elementary subatomic particle that is being measured?
Well, it just doesn't, as I said. I don't know what, so you think that an interaction with a single particle is a measurement?
No, I'm
That's
saying
just
that.
not, well, then what are you saying?
That
I don't know.
You're saying that the settings of the detector determine the measurement outcome. In other words, the settings of the detector change the thing that is measured. The setting of the camera changes the moon when I photograph the moon. Although I know it's a classical intuition, you don't want to transfer it. But essentially, for people to follow us, that's what you're saying. The thing that is measured changes depending on how I set up my detector.
No, the thing doesn't change. As I said, I don't want to introduce any new degrees of freedom. So I think the point where people get confused is that they think the hidden variables in Bell's theorem, or really in all of those other theorems, are properties of the prepared state. They're kind of little additional degrees of freedom that sit inside the particle or something. And if that's how you interpret it, then you arrive at this weird conclusion that the measurement setting at the time of measurement changes something about the particle and actually must have changed it earlier. But this is just not what the hidden variables in Bell's theorem are. The hidden variables in Bell's theorem are that what determines the outcome of the measurement. So if I only give you an initial state of a particle with whatever variables there are, if you want to add more or you just only take the normal ones, that doesn't determine the outcome. You also need the evolution law. So what I'm saying, and this is why I use this carefully phrased sentence in my video, which you just threw out, that what the particle does depends on what you measure. Okay, and what this refers to, what the particle does concretely, I'm referring to the evolution law. So if you look at, for example, if you had looked at my toy model paper, you would have seen that this is exactly what the evolution law does. The measurement setting is in the evolution law.
So the
I have a quick note, Bernardo, that may help. So instead of saying you're saying and so on, say are you saying, because this way we can find out if there's agreement.
No, I'll go along with her terminology for the sake of the discussion. What the particle does depends on the detector's settings. But the particle only interacts with a tiny measurement surface on the detector, far away from whatever else is going on in the detector. How are we to reconcile? I mean, isn't that, this is what you need to break statistical independence, but it's like saying that there is a complex causal chain between the aperture and exposure settings of my camera and the moon, so that what the moon does depends on the aperture and exposure I use on my camera when I'm photographing the moon. It's a very complex causal chain because the interaction between the moon and my camera is just the photons from the moon hitting the sensor on my camera. I think we are being asked to believe in something very non-trivial, even fantastical. If we do not have an account that tells us precisely how this happens, why this is possible, it stretches credulity, Sabine, but less than M theory.
So I think we're not making any progress on this question on what you mean by the surface of the measurement. I just don't know. As I just said, even normally in the normal decoherence paradigm and so on, a measurement is a process with a huge number of particles. You know, we're talking of the order 10 to the 23 or something, anything that causes decoherence. So I'm not exactly sure where the disagreement is. Now, you're asking exactly how does it work? Do I have a theory? No, I already told you. Right? This is exactly what I'm trying to develop. I'm trying to figure out exactly how do I write down the mathematics. And also, I should say that when you say that this is what it takes to break statistical independence, that's not true. That's my particular model. You know, there are other people who are working on different models and they have different hidden variables and have completely different ideas. So, you know, even if you don't like what I've been telling you because you think I'm crazy talking about the degrees of freedom of the detector, which I think is the only sane thing to do, then please don't also throw out all those other people's ideas because they're completely innocent.
No, it's okay. And there's nothing wrong with work in progress. Everything that has ever been created that's good and useful and proven was once a work in progress. There's nothing wrong with that whatsoever. I do feel that you are very early taking on a very strong, very committed, even combative position against almost the whole of the physics community, but you and for other people maybe, before you have something that is more substantiated. I personally feel it doesn't do service to the cause to come out so strongly, so combative, before you even know, with some degree of precision what you're talking about. That I don't think is useful, but early stage research, that's what everything has to go through. There is absolutely nothing wrong with that. Now, on the part of decoherence, in the video you put out like 3 days ago, I think the 19th, yeah, 3 days ago, which is a video addressing some experimental results that suggest that quantum mechanics is right, that the different observers can have different but true accounts of the same series of events. That's a prediction of quantum mechanics. Rovelli sort of elaborated vastly on this back in '94. And these experiments using the Wigner's friend thought experiment seem to have confirmed that. Your criticism against that is that instead of Wigner's human friends, photons were used as observers. And your criticism was, well, a photon is not a valid observer because a photon doesn't cause decoherence. But you yourself has acknowledged, like the fathers of decoherence, that decoherence doesn't solve the measurement problem. It's an operational useful rule of thumb, but it presupposes that which it aims to explain, which is the existence of a classical state around a quantum system in a superposition, into which the superposition information sort of can, I speak metaphorically here so people can understand. The information of the superposition can leak into that classical world around it, and therefore in some sense become lost because it in some sense diluted in the state of the surrounding environment. But if you discard a photon, I mean, we have detectors that are made up of a small number of elementary particles today. And they are detectors, I presume you would acknowledge, or you have to give a special place to human consciousness like Wigner himself once tried to do. So assuming that you don't do that, that you're not saying, you have to have human consciousness to be an observer, I don't see why you would establish a distinction between a slightly more complex system capable of decoherence and a photon. I think both are valid observers, and the conclusions of those experiments are valid. Physical quantities are relational. They are contextual. They are not absolute.
So, first of all, you're throwing together various different things. Maybe let me start with the first thing you said. You were complaining that express myself very strongly, I'm very combative or whatever. So I have no idea, honestly, why you would say that. I've written like 3 papers in 10 years, if that's what you call combative. I don't know what you want to
it's your
call the
videos.
people who are working on my video. Well, my video is a summary. Well, I think I only made this one video about superdeterminism. That's a summary in which I'm trying to weed out the most common misconceptions about superdeterminism. It doesn't actually say anything particular about my own work. I wouldn't do this in a video because most people wouldn't understand it anyway. So I find this a little bit weird that you would be picking on this. Now, your other question, you're asking about my video, which came out this weekend, in which I do not talk about superdeterminism. Now, you seem to be criticizing me that I don't. That's a little bit weird. Like I can't in every video tell people what's the exact thing that I'm working on at the moment and how this would affect this conclusion and so on. This is just nobody would be interested in it. Okay, so it's correct that in this video I do not talk about how this would look like from the perspective of superdeterminism, but I explain this in one of my papers if you're interested. I can send you the link to this, which is actually the reason why I was looking at those papers to begin with.
I appreciate
now, coming to decoherence, again, I just don't know what you're talking about. Like if you ever look at any decoherence formalism, it always involves an interaction with some kind of environment that has a lot of degrees of freedom. And a single photon just isn't that environment that causes decoherence. I mean, what's supposed to cause the decoherence?
Well, my point is not that it should cause decoherence. My point is, why should it cause decoherence in order to be a proper observer? Because we have these interference experiments that give us information about the superposition states. So the photon doesn't need to decohere anything for us to get information about what's going on, which is exactly what the paper by Proietti and others from Scotland did. But in your video, you say very explicitly, the photon is not a proper observer because it does not cause decoherence. And my point is, why should it need to cause decoherence? We can do an interference experiment and we can gather information without collapse while the photon is in a superposition state. And I'm bringing this up in relation to our previous discussion because it bears on what I perceive to be the same metaphysical commitment, which is the commitment that physical properties have standalone existence and therefore they are non-contextual, they are absolute, they are not relational. And it's the same topic that you addressed in your latest video, although under a new name. I don't mind that you bring superdeterminism into it. My only qualm is why throw away the entire experiment and the careful work that was done about it. I mean, you end the video with a big red cross on top of the paper saying it means nothing. And you're doing that based solely on this notion that, well, it means nothing because the photon is not a valid observer. But, since the advent of interference experiments, we don't need decoherence to have an experimental outcome. Why isn't the photo a valid observer? Why isn't the photo a good friend of Wigner?
Well, of course, you can make all kinds of measurement on photons, but those measurements would never disagree with each other. Like quantum mechanics would just give you some answers. Where the disagreement comes from between the different observers is that you disagree over exactly where the measurement happens.
But the quantum theory tells us that different observers can provide equally true but different accounts of the same sequence of events, right? We know that. That's the math of it.
But that's completely meaningless unless you explain what you mean by an observer.
An observer is any system that interacts with the thing observed in a way that changes its state.
Well, I would disagree with that. That's just in practice, that's not how we make observations.
Then what's an observer, fundamentally?
Well, that's exactly the problem that I'm trying to explain in my video. Quantum mechanics does not tell you what a measurement is.
So according to you, what is an observer?
Well, I think this whole idea of the observer is kind of irrelevant. As you already said, it kind of brings in this idea that consciousness had something to do with it. I think it's entirely sufficient when we talk about detectors. And as I already said, a detector is anything large enough to cause decoherence. That does not mean that I say decoherence is sufficient to explain what happens in a measurement. I'm just saying that that's roughly the size at which you would reasonably call the thing a detector.
But if I can do an interference experiment and gather information about the state of the photon entangled with whatever is being measured, and I gather valid, accurate information about that superposition state, why is that not a measurement? Why is the photon then not a detector? It didn't decohere?
Because you haven't collapsed the wave function. That's the whole point of a measurement, that you collapse the wave function.
But then interference experiments are invalid. We should throw them away. They don't provide valid information about a superposition state.
I don't know why you would say that.
Because the paper you were criticizing used an interference experiment to gather information about a superposition state and extract conclusions from that.
Well, sure, you can do that. I have absolutely no problem with that. You know, this also, I mean, you make it sound like I have a problem with the experiment. Experiment is fine. You know, I'm sure they're great people and they have a great laboratory and they're all nice people and what have you. I'm just saying this experiment doesn't show that objective reality doesn't exist. The conclusions are entirely unwarranted.
Well, that's the science press. Objective reality doesn't exist, all this nonsense. Let's speak technically. The experiment suggests that physical quantities are indeed relational and contextual. You seem to dismiss that conclusion.
No, I have no problem with physical quantities being relational or whatever. Also, I mean, if I may say, we were trying to talk about superdeterminism, and now we've drifted off to you trying to criticize a video that I put out on the weekend. So yeah.
Okay, what other question regarding superdeterminism do you have, Bernardo, for Sabine?
I don't want to get too much airtime. I have my little notes here.
Okay, perhaps we'll take an audience question about superdeterminism.
Okay,
I mean, unless you have one ready, because it'll take a while for the audience to see this. There's a bit of a delay.
I think I made most of the points I wanted to make.
Sabine, do you have a question for Bernardo?
Well, I'm really generally curious why people are so opposed to violating statistical independence. Like this entire story about the moon and so on, I think you are aware that this is using a macroscopic comparison for something we only ever observe in a quantum experiment, right? So of course it sounds completely crazy, right? So I don't really know why people are so willing to throw out this option of violating statistical independence. I really don't get it.
I don't think it should be thrown out, but to come out strongly and say it has to be thrown out because reality is that statistical independence doesn't hold, I think that's a very, very strong statement. And it shouldn't be made lightly, because statistical independence is something we have learned throughout the history of science is applicable. And to now suddenly depart from that, there has to be a very good rationale for that, very, very well substantiated. There's nothing wrong in being in a minority position. I am in a minority position all the time. I know very well what that feels like. But it's important to be able to substantiate very well why we are taking that minority position and saying that everybody else is wrong. I mean, I didn't want to pick on you when I said that that you were coming across very combatively. It was just as part of your video in which you say that all those old male physicists don't have a clue what they're talking about, something of that tone, which I like. I like that tone. But I think you're exposing yourself now in this specific area of your work where it's so early. But you know, keep in mind you're going against practically the entire physics community here. and you're going very strongly after them. And you're doing that before you have even the outline of a theory that can be defended. You're asking people to throw away learnings. You call them assumptions. I call them learnings that we have accumulated over hundreds of years. And I sense that you're doing that because of a metaphysical commitment, which is the very thing you are in a crusade against. Thank goodness you are in a crusade against that. And I'm with you on that crusade, and I feel slightly betrayed with your talk of hidden variables.
I don't know why you're talking about my metaphysical commitments. I tried to tell
physical
you
realism.
in the very... I don't know why you now rotating back to physical realism when I told you in the very beginning that my problem is that non-locality is not in the measurement collapse. It's not compatible with general relativity. I'm trying to solve a mathematical problem, and that's the only solution that I think works. And now all you talk about why I'm so combative and so on and so forth. I don't really know why where this conversation is going. It doesn't really make a lot of sense to me.
What is the disagreement, Bernardo, besides the strength at which, or at least perceived strength at which Sabine puts out a position? Because to me, that's an ad hominem from my perspective. Do you have an argument about the argument itself?
I think hidden variables at this stage are a fantasy, and we have absolutely no experimental reason to entertain them, or no experimental reason to depart from statistical independence, which has held for 400 years of science literally everywhere. We do not have a good empirical reason to depart from that, or a good empirical reason to postulate hidden fantastical entities that are completely counterintuitive and for which we do not have even an explicit theoretical account. So I think the whole thing is a fantasy that departs from empirical rigor.
Well, I could likewise say that it's completely insane to throw out locality, which has been historically dramatically successful, right? And also, I mean, about this, you're talking about statistical independence again. You're using a notion of statistical independence that we use in statistical mechanics and so on, which just has nothing to do with this notion of statistical independence that enters Bell's theorem. I don't even know why people think they are the same thing. They're just completely different things. Or maybe people get confused about why that it's called statistical independence. I mean, we already noticed when we were talking about what it actually means to violate statistical independence that you don't even know what it means. Right? People write down this equation. They don't know what the hidden variables are. They confuse causation with correlation. And then they come to all these weird conclusions about there having to be some kind of conspiracy and so on and so forth. Now, look, I'm a maths person, okay? So I work with equations. So all this kind of stuff, it goes right past me. What I want to know is, can I write down a theory that's internally consistent and will actually make predictions? And now you're asking, why am I saying something about it if I don't have a full theory? Well, that's actually a good question, and maybe I should spend a minute trying to answer it. It's because I've seen from what's happened in quantum gravity and also in particle physics that this idea to formulate a full theory that is mathematically consistent, and then you go and test it, just doesn't work. You need experimental guidance. And so trying to fumble together all the details without any kind of experimental evidence that you can use to build the theory just isn't going to work. And this is why I've been going around for 12 years trying to convince experimentalists to please stop doing always the same Bell-type tests, which will always give the same result, but we already know this. Please do some other experiment that could reveal some evidence for those hidden variables. And I'm very frustrated that no one wants to touch it because everyone's like, oh, superdeterminism, oh, right, that was this weird thing where you have to throw out free will, right? So they're afraid to touch it.
I agree with you, but I sympathize with them. You have to propose a minimally precise experiment. What you have proposed so far is so vague You don't know what you're controlling for. You don't know what the thresholds are.
Like Bell's theorem, right? That's also terribly vague.
No, it's very precise. The statistical...
Very precise. Well, has Bell told you what the hidden variables are in his theorem? No, he hasn't. Right. But I have to do it.
He said, what exactly is the statistical measurement, the ensemble measurement that you would expect in case local hidden variables are the case, and the difference with what quantum mechanics predicts. So the experimentalist knows exactly what to measure, under what conditions, and how to interpret the measurement. But if we are told, well, you have to cool the detector down and you have to reduce the degrees of freedom of the detector, and you have to make enough measurements in rapid succession, the experimentalist will ask, how cool, how rapid is rapid enough? What exactly do I need to measurement? And what exactly are the degrees of freedom that I am allowed to have? If there aren't answers to that question, then it's,
But I do have answers to this question in the paper that you didn't read from 2011. I've now said this a few times. There are numbers in the paper. I've actually counted the degrees of freedom. I've estimated the temperature and the size of the thing and how quickly you have to repeat the measurements and so on.
In the 2019 or 2020 paper, it was not there.
That's right, because I've already published this in an earlier paper. I don't like to plagiarize myself. And maybe I'm a little bit old-fashioned, but there's a reference in the paper which to the earlier paper where you can look up the numbers.
Maybe the experimentalists are also only looking at your latest papers and they are extracting the same conclusions I did, which is throw your hands up and say, what can I do?
Well, actually, I'm actually in touch with at least 3 experimentalists who have different ideas of how to go about it. So I'm not completely hopeless at this point that maybe it will happen within my lifetime.
Okay, let's get to an audience question. This question comes from Gastronic. It may help me, referring to Gastronic, understand the discussion of superdeterminism better if it is clear, and you already outlined this, Sabine, but perhaps it could be outlined again. What is meant by the definition of looking/not looking at and or measuring/not measuring in the context of the double slit experiment? That's what this person wrote down.
Well, as I already said, in my mind, a measurement is an interaction with an apparatus that can amplify a small signal, and that apparatus has to be large enough to cause decoherence, but I don't think that the decoherence is sufficient to actually describe the measurement process. This is what you need superdeterminism for. I hope this helps.
This question is to both of you. It comes from Salvatore Pais. Salvatore Pais wants to know, this isn't specifically about superdeterminism, but Salvatore Pais asks, if you all believe that there could be a superforce, a force of unification for all forces, that, and just so you know, Sal wrote down, Sal believes that this superforce, quote unquote, exists at all points in space and time at Planck scales and is equal to the Planck unit of force, namely c to the 4 divided by g, which in his mind has shown that the strong nuclear force equals the force of gravity, which equals the superforce. So what is your take on this? What is your opinion on this? Salvatore Pais wants to know. Bernardo, do you have any thoughts on that? And then Sabine.
Forces are models. If you don't want to talk about forces, you talk about force-carrying particles. And if you don't want to talk about particles, you talk about field excitations. These are models. The question boils down to, do I think we will one day get to a unification theory that brings gravity into the fold of what is today known as whatever the 17 quantum fields? Do I think a grand unification will be possible? Yes, I think it will be possible. It may not go along the lines of M theory. Maybe it goes along the lines of loop quantum gravity. But I think ultimately, I think nature is screaming to us that whether we know it or not, there is such a thing. Nature behaves in a unified way, such that there are no built-in contradictions in nature. So yes, I think eventually something like this will be possible.
Sabine,
do you have any opinions on Salvatore Pais' question?
No, I'd rather not. So basically, I agree. Broadly speaking, we know that nature has never shown any internal inconsistency. So at least when it comes to the problem of combining quantum field theory with general relativity, there has to be a solution to this. Now, as I have probably made clear, I think that superdeterminism is part of the answer. Now, when it comes to the unification of the other interactions, I'm not that sure. I'm not sure we actually need it. May or may not work out in the end.
Well, I know you both have to get going, so thank you all for being here. Thank you, Sabine. Thank you, Bernardo, for spending some time with myself and with the audience. And perhaps we can go through that 2011 paper at some point in the future and have a more specific and constructive conversation. Thank you so much.
Okay, thank you, guys.
Thank you.
It was at this point that Sabina had to leave, and so Bernardo stayed behind to take some audience questions one-on-one. Okay, Rad Capsule says, without thought there is no science. If one wants to apply reason and logic as the scientific method requires, one has to first know what thoughts are and where they originate. Do you agree?
Absolutely. And that's one of the weakest links in our epistemology today, in how we deal with our own knowledge. We miserably lack insight into the thinker. And we think that thoughts are objective entities that have a reality of their own, independent of the thinker. And the thinker's hidden assumptions and prejudices and commitments, and so on and so forth.
Skemson says, what evidence or reason do you have for meaning that consciousness is not evolving?
Is not what?
Not evolving.
I think the contents of consciousness are evolving. Our mental capacities are evolving. I think not so long ago, there was no capacity for metacognition in nature. Sorry, it's my allergy. So the contents of consciousness are evolving. There are more insights. There is more understanding. We have a better grip on what's going on. We're still very, very far away from a complete understanding of what's going on. I think we still make many, many, many mistakes. There are a great number of things we take for granted that are not true. I think we would be tremendously surprised by the depth of our ignorance if suddenly we became aware of it. But steps are being made. We are not where we were in the Middle Ages. We have advanced, and we've identified some common pitfalls, and we don't fall in those anymore. We fall in others still, but at least in some minds, we no longer step.
Man in Blackened Woods says, question for Bernardo, can you envision a way in which idealism can be refuted or falsified?
If one would prove that what we call physical entities, which are entirely defined by physical quantities like mass, charge, momentum, so forth. If one could prove that those have a objective and standalone reality, irrespective of the observational context, that would go some way into indicating that idealism is implausible. It might also go some way in indicating that a great many things about cognitive psychology are implausible as well, and some aspects of our colloquial materialist understanding of the world as well. So that would be one way. As it turns out, for the last 40 years, and that was a discussion we had today, precisely the opposite is what is emerging. Unless you give up on statistical independence and you presume, and you, how to say, I want to use a word that isn't disparaging, and you take on board the possibility that the settings of the camera change what the moon is or does. If you take that on board, then yes, you can say, well, physical realism, the standalone existence of physical entities has survived these experiments. But you pay a very big price for it. You have to part with something that has been reliable for the entire history of science, which is statistical independence. Or you have to take on board the notion that there are countless real, physical, parallel universes, countless, popping out every infinitesimal fraction of a second out of nowhere for no reason, for which we have absolutely zero empirical evidence. That's another way to get out of it. So ultimately, it gets down to a context of plausibility. And Sabine was correct today that science is about what can be rendered most implausible or least implausible, because whatever data you come to me with, I can always say, well, it's the hidden flying spaghetti monster that manipulated the physical world from behind the curtains. I cannot disprove that hypothesis, but it's very implausible. And I think on that same account, parting with a statistical independence in the name of hidden variables for which we have no empirical evidence is implausible. And multi-universes popping out of nowhere for no reason, every infinitesimal fraction of a second, is implausible. And what remains on the table is very, very, very plausible, completely intuitive. Physical entities are the outcome of measurement, just as the indications on the dials of a dashboard are the outcome of measurement. If you don't measure, the dials show nothing. If you don't measure, there is no physical world. But what is the thing that is being measured? That's the question. That's where we are going to make progress. If we heed what 40 years of experiments are telling us, if we heed that message, we understand that there is a deeper layer of reality whose appearance is physicality, but not the essence. The essence is something else. Physics is relative to that deeper layer. And I believe we may even arrive eventually at a deterministic theory of nature if we start investigating that deeper layer without holding on to our metaphysical prejudices that physicality should be the end of the story, because it's holding on to that will prevent us from making progress. If we don't heed the results of experiments, but keep on fighting with experiments based on very implausible hypotheses, we will slow down progress. We will not stop. Eventually, this whole thing will fizzle out. Fantasy cannot last forever, but it will slow it down.
Daijin CPPL wants to know thoughts on Joscha Bach's theory of consciousness. That's a question for you.
I don't know what progress he has made since I had an interaction, I think, with this Joscha Bach on my forum years ago, 2016, I think. But in 2016, if this is the correct Joscha Bach, I don't know what he's smoked. I think it's nonsensical. I think it's equivalent to saying that if I simulate kidney function on my computer accurately enough, my computer will urinate on my desk. You can only extract that conclusion if you mistake the difference between a simulation and the thing simulated. If you forget to see that a simulation is not the thing simulated, then maybe you will have artificial consciousness in a silicon computer. But the plausibility of that is exactly the same as the plausibility that my computer will urinate on my desk if I run an accurate kidney function simulation on it.
All right. Well, great talking to you again, Bernardo. We'll talk over WhatsApp. And if you don't mind, you'll have to log yourself out. I can't kick you out because I don't know how to do that without banning you.
Thanks for having me, man. It was a pleasure. Take care.
Pleasure's all mine, man. Okay, everyone. Yeah, some people want to know if that was the Salvatore Pais who asked that question. Yes, that's true. He is indeed real. He's a person. He's a perfervid and jolly fellow. We recorded some small conversations already, about 15 minutes, maybe 30 minutes worth of extra material to go at the end of our conversation once we do have our live conversation, because usually what happens is I privatize the live recordings, which I'm going to do here, and add extra footage, improve the quality, add a Patreon request, etc. Speaking of a Patreon request, if this is the sort of content that you enjoy and want to see more of, and you have the means and the want, then please do consider going to patreon.com/kurtjaimungal. It's a significant amount of work to put some of these on. Sometimes they take weeks, So for example, with Sal, I want to go through his patents to do them justice, and that's going to take quite some time. The reason that Sal reached out to myself and not others will make sense once the interview is conducted, as well as the reason for the interview being pushed to March will make sense as well. If you're listening to this on the audio platforms, I know that right now you're watching, but if you're listening to this on the audio platforms, please do leave a review on whichever platform you're on, whether it's iTunes, Google, Spotify. It greatly aids the distribution. I don't think you can leave reviews on Spotify. And if you're watching this and you had no clue that there was the audio platform versions, then search Theories of Everything plus whatever audio platform it is that is of your choice. So iTunes, Pandora, you can find it, as well as the links to them are in the description generally in each video. Okay, thank you all for being here. I should get going. Take care, everyone. Thank you. Again, thank you. The podcast is now finished. If you'd like to support conversations like this, then do consider going to patreon.com/CurtJaimungal. That is Kurt Jaimungal. It's support from the patrons and from the sponsors that allow me to do this full time. Every dollar helps tremendously. Thank you.